Wait, that's what I got. What?
You always do. It's true.
She's
Calm down.
It's a bro girl takeover.
To be like you.
Leave the euphoria. Come with the bros.
Sometimes I think are they awesome?
Guys, come on.
This year.
No, I'm not.
But now it's like.
I was correct.
That's surprising.
What are you doing?
Rachel's doing great. Really great. All right, everyone, let me have you face forward. This is incredibly important for your quiz, so this is your time to ask questions if you have any. And also, I'm going to go through and grade this, not literally, but go through the details that I will be grading and looking for your quiz. So, Ben, close that laptop for me, please. So, first thing is to draw a force body diagram. And in this scenario, we've got an object at the bottom of a hill. And our force body diagram, we're going to imagine, as we did in worksheet 1, that it's just coasting due to inertia, so no forward forces and no frictional forces pulling backward, but that we have the force of Earth and the normal force, or the force of the ground, or the motorcycle pushing up on the object. Now, in this scenario, even though the person is moving at a constant speed, there is circular motion, which means unbalanced forces. And this group did a really good job of showing that the normal force is the force that is pointing toward the center of the circle, which means it needs to be bigger than the force of Earth. This is a beautiful force body diagram, but I'm missing some details. What am I missing here, everybody? Alexa, we need an X and a Y. I'm also missing another detail, and a lot of students actually lose points for this because they don't read the question carefully enough. What am I missing?
Constant velocity.
We've got a constant velocity, but that's not necessarily missing in the diagram. Audrey? The sum of the forces equations. I don't have forces on the x-axis, but I still need to show the forces on the x-axis equals 0. What I do have are the sum of the forces on the y-axis, and that's the normal force on the Vespa plus the force of Earth on the Vespa. And is this equal to 0? Definitely not. You can put does not equal 0, or you can put that it equals MA, because we're going to need that in problem number 5. Question.
Why are they balancing?
So it's moving at a constant speed in this direction, but unbalanced forces also includes anything that's changing direction. And the fact that it's going over a curve in the hill means that there's got to be some unbalanced force causing it to go through the curve. So anything that goes in circular motion, whether it's at a constant speed or not, is going to have an unbalanced force and a centripetal acceleration. Now we want to keep in mind the word centripetal force and centripetal acceleration. The beginning of it is center, meaning it should point toward the center of the circle. So in this case, the center of the circle is up. But if I had the scenario in your worksheet where the hill looked like this, where would my net centripetal force be pointing in? It would be pointing toward the center of the circle, which in this case is down. So we're sticking with this force body diagram. This one would have a bigger force of Earth and a smaller normal force. And let's move on to calculation of the force of Earth. So the force of Earth is an equation we've used many, many times in Unit 1. It's negative 9.8 times mass. This simplifies down to negative 4,900 newtons. If you use the unit kilogram meters per second squared, because this is in terms of meters per second squared and kilograms, that would be fine as well. So this group used newtons per kilogram, but you can also substitute meters per second squared in there. The next question is focused on calculating centripetal acceleration. This is in your physics helper. V squared over R, and both of those values are given to you. I want to see the guess method for these problems. I don't necessarily need it for problem number 2, because we've been doing this so many times, but I do want it for 3, 4, and 5. So the guess method includes what's given, velocity and radius. What's unknown, we're solving for acceleration, so that's our unknown value. This is our given value. And then our equation is right here. Excuse me. If you don't plug in the equation and just jump straight to plugging in these values, I'll give you both points for it. But your final answer is 6.4 meters per second squared. And the acceleration is directly proportional to the net force. And so if the net force is pointing up, the acceleration should also be pointing up. If I had this same calculation for this scenario, what would I need to add to my answer? Even though it's not included? Jack.
Negative.
You would want to add the negative. It's not going to tell you in the problem that the answer should have a negative value. You have to look at your force body diagram and add the negative after the fact. But that's only if we have this scenario and not for our actual problem, which is this scenario. Any questions on acceleration? Next one, we have to calculate the force. This group did a good job of writing the equation. We still have to include the givens. And since the givens are the same here, I'm going to say it's okay for your quiz to say that the givens are going to be the same as part 3. And then we're going to use this as a given value as well, that the acceleration is 6.4 meters per second squared. Because these are all the same part, or these are all different parts of the same scenario. So we've got an acceleration. Our unknown this time is the centripetal force, so I do want to see the guess method. I've got my equation, and then I'm plugging in my values. I'm using the acceleration from here, the mass that's given to me from the problem, and I get 3,200 newtons. Again, if I had the top of the hill instead of the bottom of the hill, what would I have to include in my answer? What would I have to include again? Negative. Good. Final problem, this is the one most students struggle with, is solving for one of the forces, because we need to use this equation and we need to use the F equals ma equation and combine them together. So we get the normal force plus the force of Earth is equal to mass times acceleration. We have the force of Earth from part 2, and we have this calculation actually from part 4. So you don't necessarily have to do all of this over again. You can just plug in the 3,200 newtons. And then because this is negative, I want to add the 4,900 to both sides. That gives me an even bigger force of 8,100 newtons. And the way you check your answer is you look back at your force body diagram and you make sure that the force of Earth has a force that is less than the force normal because you showed that the normal force should be the greater force value because it is pointing toward the center of the circle. And if you didn't get a number that was greater based on your force body diagram, you either messed up in your sign somewhere in your work or you messed up your force body diagram somehow. Questions? All right. Let's go ahead and clear off our tables. All right, let me have you pull out worksheet 1 because we didn't finish this worksheet. And we're going to first look at page 2. There was part H and problem number 1. And it talks about suppose the car were going faster than the speed you calculated for 1g. So the speed we calculated for 1g really quickly is assuming that the centripetal acceleration equals the acceleration due to gravity. So in this scenario, we have the normal force and the force of Earth equals negative 9.8, which is the acceleration due to gravity, times the mass. The problem is that the force of Earth also equals negative 9.8 times the mass. So if I end up with this scenario where the normal force plus the force of gravity or the force of Earth equals the force of Earth, I would end up adding these two values together. And what force do I get for my normal force? I get 0. That's really weird. So now my force body diagram as I'm going over the hill is the force of Earth. And this normal force gets smaller and smaller and smaller the faster you accelerate until it reaches 0. So what happens if we actually go faster than the acceleration due to gravity? What's going to happen to the normal force then? Alexa. This is a sensation you feel when you're actually flying out of your seat because you've driven too fast over a hill. Or if you guys are going on a roller coaster, there's a reason why they strap you down, even if it's not a roller coaster that goes upside down, because you fly out of your seat. So what is actually happening here? We know that our acceleration is equal to velocity squared over the radius. If our acceleration is beyond the negative 9.8 meters per second, what ends up happening is the radius of our circle is actually decreasing, or our velocity is increasing, but it's causing the radius of our circle to increase as well. So then, as, let's say this is our car, and this is us, as our car is driving over the hill, it's actually driving over a radius that's even bigger than the hill itself. And so our body ends up following this circular motion rather than the circular motion of the car itself. And that's when our butts start lifting off the seat, and then you start getting that funny feeling in your tummy because of that high acceleration. So I wanted to talk about part H just because it's an interesting concept about circular motion, that once you exceed the force that Earth pulls you down onto your seat, you actually fly out of your seat because your normal force is no longer existent. Any questions on this? Okay, let's jump to part 3, which is a circular motion, but this time it's not a hill. It's a circular motion when you're traveling around horizontally rather than vertically, right? So imagine you're getting off the off-ramp and you're here at this star. So you've traveled around in circular motion in this direction and you're looking at the car from behind. It's different than the force body diagrams where we had just the force of Earth and just the normal force, because now our horizontal motion is going in the X direction, not the Y direction. So I want you to keep in mind the concept that centripetal forces always go toward the centripetal, meaning center of the circle. The acceleration is directly proportional to the centripetal force, and therefore the centripetal acceleration is also pointing in toward the center of the circle. And then the rest of these calculations should be straightforward based on your formulas in your physics helper. The one that's not straightforward is D, because it has a mu value, which even though we talked about frictional force, we never calculated it using the friction equation. So go ahead and drop out D. And then we've got 4, which talks about G's. You probably heard of the term G's before if you've watched Top Gun or any sort of movie where they're moving at really, really fast speeds. G is exactly what we know G to be, which is negative 9.8. It's the acceleration due to gravity. But now we use it as a term for really, really high speeds where we're traveling at 7 Gs in this scenario, which is 7 times the acceleration due to gravity. So all this question is asking you to do is calculate the speed given that the acceleration is negative 9.8 times 7. 7 times your acceleration due to gravity. And then you've got everything else you need. You've got your radius, your acceleration, and you're solving for speed. So this worksheet should be pretty straightforward. The lab itself is going to be focused on gravitational motion. Problem is we can't do labs with the planetary motion of Earth except through simulation. So no hands-on activities for this. We want to get into the Canvas. Under Kepler's Law Lab, you have a link in your worksheet, but I have linked it in this assignment so you don't have to type up that HTTP URL. And then it'll take you to a simulation that goes over Kepler's 3 laws. And you're going to play around with this to make some observations on what Kepler discovered about planetary motion. So, planetary motion might look like they're traveling in a circle, but it's actually planets traveling around the sun in an ellipse. So the eccentricity, not eccentric, but eccentricity represents how narrow your ellipse is and how circular it is. And I want you to notice the more narrow the ellipse is, the sun actually isn't in the center of the ellipse. It's called a focus. And we'll talk about how ellipses have 2 foci because you need 2 to create an ellipse, and we'll do that demo next class. First of all, you're going to play around with A, which is your semi-major axis. You can create a bigger radius and a smaller radius, and then you can change the eccentricity as well. But I want to make sure that you include all of these check marks. So it might look like a really long lab, but the lab itself is just a list of a bunch of instructions. All right? And then the next thing you want to do is write down the values. It says R1 and R2. That's these values down here. And then it's going to have you move your planet around. And I want you to reflect on how the R1 and R2 change, as well as the total, how that changes. Kepler's second law is related to sweeps. And sweeps are an area of a planet's motion in a certain amount of time. So I want you to notice, I'm just going to clear the screen, but I want you to notice if I start the animation and I add a sweep, that it's going to highlight the area of this motion, but then as I move this area around, notice how the closer it is to my orbit, the fatter it gets. The further away it is, the more narrow. And I want you to pay attention to the sweep area, how that changes as you move it around. The other thing I want you to notice, and it's hard to notice when it's going this slow, but if I move it faster, I want you to notice how the speed changes. And think about its location relative to the sun. And then last but not least, you've got Kepler's third law. Kepler's third law gives you an equation here, and you're going to fill out a data table. But the equation gives you p squared. The squared is actually in the wrong spot, and that confused students. But 2.96 squared is equal to 8.74. 2.06 cubed is also equal to 8.74. So in your data table, when it asks you for P, that's your period, then I want you to put the 2.96, but if it asks you for P squared, I want you to put that total. That's right below it. Because I want you to understand that the P and the A are related to each other in terms of those two powers, P squared and A cubed. And then they're going to ask you to choose certain planets. So you're going to start with Earth, hit OK, and then you're going to notice Earth is pretty circular. Not a perfect circle, it's still an ellipse, but pretty circular. They're going to ask you to change it to, I think it's Mercury. And then they're going to give you two planets that are non-existent, but what you want to do is try to create an eccentricity that matches that planet and make sure that the period matches as well so that you can get all the other values in your data table. The very last page we're going to reflect on as a class, so you don't have to worry about doing the new Kepler's 3 laws until next class when I see you.